Let's jump right into it. Acids and bases. So chemists usually use, there's actually three. In this class we talk about two definitions of acids and bases, and they are the older Arrhenius definition, and this was put forth by a chemist by the name of Svante Arrhenius, whose name is just really fun to say, Svante. He defined an acid as a substance that produces hydronium ions, H3O+. These will become your friends over the next couple of semesters. When added to water. Now this hydronium is sometimes simplified as merely a proton, H+. Bases in the scheme are defined as things that create hydroxide ions when that substance is added to water. A little bit later came the Bronsted-Lowry definition, which is a little more general, and it's not talking about a specific species, nor is it talking about a specific solvent. A Bronsted-Lowry is a substance that donates a proton to another species, and a base in the Bronsted-Lowry definition is something that accepts said proton from another species. All right, so let's jump into it. So here I've got 4 acid-base reactions, and what I'm going to ask you to do is, choosing from the reactants, pick the Arrhenius acid and the Arrhenius base. And usually if someone is asking you pick the acid or base, it's usually going to be from the reactants. Let's get the pen up here. All right, so let's look at this reaction here. We've got HCl, which is a gas at room temperature and pressure, reacting with liquid water to give us hydronium and chloride. And so for the Arrhenius definitions, acids were considered something that makes hydronium when mixed with water or reacted with water. So this is going to be an Arrhenius acid. Now ammonia, NH3, again also a gas at room temperature and pressure, reacts with water to form ammonium and hydroxide. And hydroxide was the hallmark for something being an Arrhenius base, or the production of hydroxide. So now we have HCN, and when reacted with water it gives us hydronium and CN, so HCN is an Arrhenius acid. So HCl, NH3, HCN. And finally, hydrogen carbonate, or bicarbonate, as this is often called, reacts with water to form carbonate and hydronium. So this too is going to be an Arrhenius acid. Now note that in every case, in all of these reactions, there is only one acid or base. So now to contrast with the other definition, we're going to look at the same 4 acid-base reactions, and again, picking from the reactants, determine what, if any, Bronsted-Lowry acids there are, and what, if any, Bronsted-Lowry bases there are. Again, remember, these are the same reactions. So now you have to get used to looking at what the products of proton transfer reactions are. So I'm going to go through the first one with you and then let you think about the other 3 on your own. All right, so let's look at this right here. So we've got HCl and H2O as the reactants. We have H3O+ and Cl- as the products. So think about what happens. Let's see, let's clear out of the way there. So how would you go from H2O, let's say, to H3O+? Well, you would pick up a proton, and again, how do you key in on that? So the formula has increased by 1 hydrogen and the charge has gone up by 1, and adding an H+ to a species does that. Now let's look at HCl, and so let's kind of follow the chlorine, right? So this HCl ends up as chloride. So it apparently lost a proton. If you take a proton off of HCl, you lose an H from the formula and the charge goes down by 1. So clearly a proton went from HCl to H2O, and that's the proton transfer. And if the proton went from HCl to H2O, then this guy here is going to be our Bronsted, that's an L, believe it or not, Lowry acid. And this guy right here is the Bronsted-Lowry base. Now, using that as a model, hit pause and look at the other three. All right, welcome back. So in this case, if you want to think about the direction of proton transfer, so look at the differences between, let's say, the nitrogen-containing reactant and product. And the NH3 became NH4, picked up a proton, charge went up by 1. So, and look at the water right here. So the other oxygen-containing compound on the product side, sorry, is hydroxide. And how do you go from H2O to OH-? You lose a proton. So apparently, in this case, the direction of the proton transfer is this way, which makes water the Bronsted-Lowry acid and the ammonia the Bronsted-Lowry base. For HCN, it looks like the proton transfer went from the HCN to the water to make hydronium and cyanide. So in this case, we've got the Bronsted-Lowry acid, and here we've got the Bronsted-Lowry base. And for the last one, again, it looks like the proton went from the bicarbonate to the water. And so again, the bicarbonate is going to be the Bronsted-Lowry acid, and the water is the Bronsted-Lowry base. All right, so they've all been labeled. A couple of things to note. That all of these reactions have an acid and a base. Now, this is an aspect of the fact that in the Bronsted-Lowry definition, you're talking about a transfer of proton. So something's got to give it up, the acid, and something has to take it, the base. It doesn't just, exist on its own. So in the Bronsted-Lowry definition, you always have to have an acid and a base in any reaction. All right, so same 4 reactions. I've cleaned up the scribbling here a little bit. I've still got them labeled as either a Bronsted-Lowry acid or base. Next question. Can something be both an acid or a base? Now, normally you think of them as being complete opposites, but take a look. And the answer is, turns out, yes. And water, in these examples, is acting as an acid in the second reaction, and it's acting as a base in the other 3. So what it turns out is that acid or base behavior is sort of a relative thing. And substances that can easily act as both are referred to as amphoteric, and water is a very good example of that. So water is perfectly happy acting as a base in the presence of a stronger acid, and it's also perfectly happy as a acid in the presence of a stronger base.